If I import some results from AXISVM to Grasshopper, the received information is always organized into a data tree. Now I'm going to explain the logic behind these data trees and show some examples how to handle the results in Grasshopper. I begin with the system used for the result cases. This is common for each imported result type. If my result case input is a simple load case, the data tree at the X result case output is represented by a single straight line in the param viewer. Path 000 is assigned to it. The original result case list consists of 9 items. It comes from a linear static analysis of a steel frame structure. I add the index of the critical case to my selection. Thus, I have 2 branches in the param viewer. The load case is still on path 000 and the critical case is on path 100. Let me lock the solver for a second and connect 2 more result components. Then remove the lock. And you can see that the second index of the path is increasing as we go over the different result components. And the visualization shows the 3 separate branches as well. If I change the min-max type input from min to min-max, the getResults component automatically splits this into min and max result case for each result component. Therefore, the last index of the path is changed to 0, 1, 0, 1, and so on to distinguish between these cases. Path indices always start from 0 on the output of this component, and the order of the result cases is determined based on the order on the input side. The param viewer shows that there are two sub-branches at each result component. Okay, quick summary. So the path of the output result cases contains always 3 indices. First one stands for the result case, the second for the result component, and the third for the min-max type. Inside the encircled region, the data tree is always built with this logic. This is completely common for all available result types. The item IDs and the result values are going to be added outside this circle. To provide more details about the data trees of the imported results, I take first the result type with the most simple data structure, the nodal displacements. First, I connect a panel to show the text description, and you can see that I have 3 result cases and 1 node. Then I go to the results subcategory and take the AXISVM deconstruct results component to get access directly to the result values. This component accepts 1 result type at once. If I connect the X result output to it, the output parameter names and descriptions are automatically adjusted, and the result type name is displayed in the message balloon at the bottom of the component. I show the contents of some output parameters. In the panels, you can see the result cases, the node ID I currently work with, and the displacement values in X and Y direction at node number 8 as data trees. If I merge the output values except of the output called header, I'm going to have an overview of the complete data tree. In this case, the paths with 3 indices represent the 3 result cases. The paths with 4 indices represent the node ID lists in each result case, and the paths with 5 indices represent each result component for each result case. We have 8 result components for nodal displacement. Therefore, we have 8 sub-branches here. I split this data tree and focus on the results belong to the first result case only. I show the contents in a panel, and you see that we have one single value in each branch. Then I lock the solver for a second and add 2 more nodes to my list. Look at the param viewer. Nothing has changed there. The reason of this is that the node IDs are stored in a common branch as data list, and the result components are stored the same way. For example, the displacement in x direction is stored in a list for node number 8, 9, 10 in this order. To make it more clear, you see the encircled region that contains the information about the result cases. The next level contains the node IDs, and the following 8 sub-branches contain the result components. Very similar data structure is used for the nodal support reaction forces. The next example shows the data structure of the structural member internal forces. This data tree is set up for 2 result cases and 8 truss members, and we have 7 available result components on the output side. Let me show the AXISVM model. I talk about these 8 diagonal truss members of the structure. This data tree is a bit more complex. I have separate branches for each truss member. The truss member is represented with one single line and one single section. Therefore, the data tree continues with straight lines. Then, at the end, it is broken into 7 sub-branches for the result components. Now I change the input and request results for 2 beam members. These beam structural members are split into 8 finite elements during meshing. This is why I have 8 sub-branches. These sub-branches contain the section positions in the local coordinate system of the member as data lists. Similar to what we saw at the nodal displacement, that we have more values in a common branch. For the section lists of each finite element, we have the already mentioned 7 sub-branches for the result components. Similar data structure is used for line and member displacement, line internal force, and line support reaction force as well. The last representative example shows the structural member stresses for one single result case and for 8 truss members. Since the truss member is represented by one finite element and one section, there's again a straight line in the param viewer that leads to the 15 sub-branches of the result components. If I change the input to 2 beam structural members, I see that both members are split into 8 finite elements in this example, and each finite element has 11 sections now. Compared to the data tree of the member internal forces, it's new that each section has also its own sub-branch, and these are broken into further 15 sub-branches representing the result components. This is required to be able to store the results at each stress calculation points of the sections. I'm going to make further clarification about this later on in this video, but now I rather want to explain that the lines expression is in brackets on the param viewer because that intermediate path is not really a part of the data tree. You can see that I don't have any branch path with 5 indices, but the 5th index of the section paths is growing from 0 to 7 to group the sections according to the finite element mesh. Last but not least, I mentioned that similar data structure is used, of course, for line stresses as well. Okay, I finished the introduction of the data structure itself, and now I show some practical examples how to work with the data. I begin this part again with the nodal displacements. I have 2 result cases and 4 nodes in this example. I haven't talked about the very first output parameter of the deconstruct results component yet. This is called header because it contains the list of all other output parameter names. Thus, it may be used as a table header. The second output is always the result case, followed by the item IDs and sections if relevant. After these, the result components come one after each other. I connect every single output to a panel to show all the contents of the component in an organized way. The dimension of these output values may differ from the dimensions you use in AXISVM. The dimension of the result values may be found in the description of the X result output and in the description of each output of the deconstruct results component. The displacements on the screen are in meters and the rotations are in radians anyway. You may have recognized that the nickname of each panel had been adjusted to the output parameter name as I connected them. This is the default behavior. And if you right-click on the component and deselect the Adjust Panel Nicknames option of the pop-up menu, every nickname is changed to Panel. This feature affects only those panels that are directly connected to the output parameters and no intermediate components are inserted. I activate this feature again for better understanding. And I mention here that the dimension of the result component is not displayed in the panel nickname because we wanted to avoid to let there any misleading text if user may divide or multiply the result values in the meantime. I show how to copy the data manually into an Excel table. I use the copy data only feature of the panels and paste the data somewhere. For the first paste, somehow I have limited options to format the data. Therefore, I use the Ctrl+C combination to copy again and paste the data into cell A now. Then I choose the transposing from the special paste options and then remove the unnecessary text. You may realize that the result case panel contains only 2 lines. But I have 4 nodes per result case, and if I want to have a correct table, I need to have each result case name 4 times. Therefore, I take the length of the node ID list and tell the result case output to be repeated 4 times. I copy the data, and to remove the extra lines, I use a special pasting process again. Here we are. The paste of the numerical values goes simply. Just the number formatting must be adjusted by the user. With this method, we get a, so to say, offline table that is not automatically updated with any changes in the data. After the nodal displacements, I talk about the structural member internal forces. The panels on the right side are connected with invisible wires to the appropriate outputs of the deconstruct results component. You can see in the panels that for truss members we have a very simple situation because one section and one result value belongs to each member. I mean, the data count is the same in these branches and no adjustment is required if you want to make a table from the data. In case of beam structural members, it's obvious that we see more sections than member IDs. To calculate how many sections belong to each member, first, I merge the 3 relevant outputs of the deconstruct results component. The outermost branches contain the section lists grouped according to the finite elements of the structural member. As I mentioned earlier, in this example, each structural member is divided into 8 finite element lines during meshing, and each line consists of 11 sections. To automatize the calculation, I use the path mapper component, where you can see that the input data of the path mapper, the section output parameter, has paths with 5 indices, A, B, C, D, E. I want to know how many sections belong to one structural member. Therefore, I remove letter E from the right side. This means that I merge all the section subbranches to the level of their structural member. You see A, B, C, D. You can check also here that structural member paths have 4 indices really. The tree statistics show that we have the required 4 branches and we have 88 sections per structural member. We know that this is correct since the 8 finite elements per member multiplied by 11 sections is exactly 88. So I take the member IDs, tell them to be repeated 88 times inside the branches. It is important that I have a data tree on the first input and I have a data list on the second input called length, and I must graft the length input to get really what I want. Now let me talk about the most complex data structure as well. If I connect the structural member stress results to the AXISVM deconstruct results component, the output parameters are adjusted, but I get a warning message. This tells me that the output count is less than the available result component count. I can solve this using the Match Outputs feature from the component pop-up menu. This expands the component and displays all available outputs. Below the section output, you can find the minimum, maximum, and mean stress components of the given section. Then, the SCP-ID output contains the list of stress calculation point IDs that belong to the given section. And then the detailed result components are available in each stress calculation point of the section. Let me represent this by connecting the member ID, the section, the SMIN, the SCP ID, and the SSCP outputs to separate panels. Currently, we see the results for a truss member, that's why it's very clear and simple. One section and one stress calculation point per section belongs to each member. If I change the input to beam structural members, the data contents of the panels are quite different. Here you can see that, for example, 9 stress calculation points belong to the section number 0. I have already shown how to repeat data, therefore now I would like to do something else. Let me say that I'm looking for the results in the stress calculation point number 1 of each section. So, using the index 0, referring to the very first item of a list, I take the first item in each branch of the SCP-ID output and the first item of each branch of the SSCP output, and I display the outcome in the last 2 panels to get an overview. As a closure, I gathered some useful components to work with the introduced data structure. The param viewer from the params tab utils subcategory often helps to understand the relation of branches, and the other 6 components from the sets tab help to modify the data count or filter the results. From other add-ons, you may try to use the heteroptera min-max component when searching for an extreme value. and the Write to Excel component from TT Toolbox to export some data into Excel sheets. Thank you for watching.